Back with our curve sketching example in section 4.4, and we are moving on to the first derivative portions of this curve sketching process. So just to quickly remind us what our function was, we are looking at the function f of x equals x to the 5/3 minus 5x to the 2/3. It's up at the top of the page here, but I just figured I'd bring it down so we can see it. All right, and notice how I am using it in its original form with the rational exponents rather than one of the radical forms or factored forms that we had also found in the last video. And I'm doing this because the rational exponent form is so much better for taking the derivative and using the power rule. So we would have just had to rewrite those other forms anyway. Okay, so yeah, let's take our first derivative here, f prime of x, and just with some power rule, that's going to be 5/3 x to the 2/3 power minus, that would be 10/3 x to the negative 1/3 power. Okay. Now, this is the derivative of the function. We have taken the derivative at this stage, but it is going to be advantageous to do a little bit of rewriting on this to help us look for our critical points. We're going to try and factor this down, simplify it, get it as good looking as possible so that we can identify our critical points and use that to find our increasing and decreasing intervals. Okay, so I am going to factor out the, let's see, well, I want to take out the lowest power of x, but I'm also going to take out 5/3, just looking at the fractions there, just to make those a little more manageable, let's say. So I'm going to factor out 5/3 and the lowest power of x, which would be x to the negative 1/3. Okay, so when we do that, in our first term here, we've totally taken out the 5/3, okay. And then our remaining part would be x to the 2/3 divided by x to the negative 1/3. And so you'd subtract those exponents and that would end up giving us 2/3 minus negative 1/3. So you end up getting x to the 3/3 or just x to the first power. Okay, so we just get left with x here. And then on our next term, we have, well, the factor of 2 for that 10/3. And then the x to the 1/3 has already been factored out. So that's gone. We're just left with the 2. Okay, so we have 5/3 x to the negative 1/3 times x minus 2. And then I'm just going to put this in a rational form, write it as a rational function. That way we can see the numerator and denominator clearly. So the 5 and the x minus 2 will be in the numerator. And then 3 and x to the 1/3 will be down in the denominator. Okay, so that's a pretty nice form of the derivative to work with. We can use that for our critical points. Okay, because we want to see where the first derivative is undefined. Right, that would be where the denominator equals 0. 3x to the 1/3 equals 0. And there's only one value that's going to make that happen. It's x equals 0. And then looking at where the first derivative equals 0, you end up just focusing on the numerator. 5 times x minus 2 equals 0. And the value that makes that happen is x equals 2. Okay, so now that we've got those critical points, we can set up our first derivative number line for testing. So let's do it. There we go. Okay, label this f prime of x. You might want to put your derivative function there as well, 5x minus 2, 3, and then I'm going to write that as the cube root of x for the testing purposes, because that's a little easier for me to think about. As far as positive and negative signs, I like thinking about it as a cube root instead of a 1/3 exponent. You might feel the same way. And let's stick our critical points on here. These number lines sure as heck don't have to be to scale. So there's 0 and there's 2. And then let's see, at 0, our first derivative was undefined. And at 2, our first derivative equaled 0. Okay, I just like making those little notes so that we can check on our graph later and make sure that, you know, things are falling where they should. Like, what could the shape of the graph look like to make this first derivative undefined? We'll see later. Okay, so now it's time for some sign analysis. So over here in this interval, pick a number, any negative number you want, and we are going to check the signs of our factors. The 5, of course, is positive. Negative number minus 2 is going to be negative. 3 is positive. And the cube root of any negative number is going to be negative. So you have a negative divided by a negative, which gives you a positive first derivative overall. Okay. Now in the middle here, pick some value between 0 and 2. Like maybe think of the number 1, for instance. That'd be a fine choice. All we really need is the signs though. Positive, number minus 2, that would still be negative there. 3 is still positive, and then the cube root of this number, whatever you're looking at in there, should be positive because this is in the positive numbers now. So positive. Okay, so you get a negative divided by a positive, which would give you a negative first derivative overall. Okay, last one. Pick any number that's bigger than 2. And the 5 is positive. A number greater than 2 minus 2 is going to be positive. 3 is positive. And these are still positive values over here, so the cube root is still going to be positive. Okay, all positives there. We got a positive first derivative. Okay, so from that, we can identify our intervals of increase and decrease. So this function is increasing wherever we have a positive first derivative. Okay, so that would be right here and right here. So that would be from negative infinity up to 0. And then 2 to infinity. And remember that you can use the union symbol right there between your intervals, or if you're on My Math Lab, put a comma for them, they like it. Okay, so there's increasing, and then decreasing is going to be, of course, our remaining interval there in the middle from 0 to 2. So we have increasing, decreasing, and increasing again. Okay, so that is going to roll right into the next part of the problem here, finding any local maximum or minimum values of the function. Now that we've gotten our first derivative chart made here, we can see where we would have maxes and mins. Okay, now note that the function itself, f of x, had a domain that included all real numbers. So none of these values of x are going to be undefined in terms of the original function. So the function is defined everywhere. we do have a place here where the derivative is undefined, but we'll still have a point on the function right there. There's not like a hole in the graph or something. Just wanted to note that. Because we can see around that critical point there, we have an increasing function, and then on the other side, it switches to decreasing. So that would indicate that this critical point is going to give us a local maximum. So a local max is going to be when x equals 0. And if you'll remember our function, there it is. F of 0 is just 0. Okay, so there's a local max at the origin, which, if you'll recall, was also our y-intercept and one of our x-intercepts. So it's going to be a nice intercept, and it happens to be a local max as well. Okay, now for the other, a local minimum, you might be able to guess where we'll have one of those. It's at our other critical point because the function is decreasing and then it switches to increasing. So a local minimum will be f of 2. And yeah, this is a little bit of a mess here. Plug it into that original function. That'd be 2 to the 5/3 power minus 5 times 2 to the 2/3 power. What fun. Okay, put that in your calculator. So this should equal approximately -4.8. There are some ways that you could have simplified this with the radicals in there, but I'll at least give you a standard calculator for these. I don't know about a scientific calculator for these problems because I don't want you just like graphing it on there. We'll see. So there's our local minimum value. Okay, so local max, local min, and then in the next video, we'll do our second derivative and look at concavity.